Sorry. Okay. I see that not everybody is signed up in WebAssign yet. Like out of the 23 students, 19 have at least logged in. Is anyone having technical issues?
Some people.
Or not WebAssign, MyLabs Plus, whatever the software is. Yes.
Yeah, I'm having on mine it's telling me that I have to, first I couldn't even get on it, and then today it told me I had to buy the code again, which, I mean, the same book and everything, I wouldn't have to.
Yeah, you're not supposed to have to. Have you contacted Pearson about it?
No, because, I mean, I just realized it was sitting in the hallway like 10 minutes ago.
Okay.
And I tried to get on it, but other than that, it's just been like, cite and spell, can't get on it at all. Or nothing comes up on the screen, and then it just told me I have to buy the code.
Yeah, because yesterday we were having problems across the board, which I'm hearing have been resolved, but I'm not sure if that's really true. But we have a situation come up, like for instance, in other classes where you use WebAssign, where someone should be able to use their code, and they fix it so that they can. So they should be able to take care of that for you. But if something comes up with that, just let me know. Yeah. So it's a between you and Pearson issue, unfortunately. It's not something that I'm able to fix myself. But with the homework due on Friday, if the extension is needed, especially for these kind of technical issues, that's no problem. Anyone else? Okay. All right. Now, any difficulties with the problems? So assuming you're getting to Pearson, I know some people have already completed the assignment. That's good, but so you want to have questions about those?
Referring to 13.2 or 13.2?
Yeah, 13.2. Yeah. Okay. All right. All's well with that one, or maybe you haven't started yet. And if not, please do soon. Being due Friday and all. Okay. 1, 2, 3, 4. Okay. Looks like everybody's here today. Good deal. All right. So we can continue where we left off last time with partial derivatives, and I have started an example about that. Okay. Apparently there's no decent chalk here. So, the example that we have is our function f of x, y is natural log of x, that can be x is not squared, x plus y squared. And how far we got last time was first partial derivatives. With respect to x was 1 over x plus y squared, and then the f dy was 2y over x plus y squared. And then fxx was minus 1. So to see where it came from, we take the derivative with respect to x that we already have, fx, differentiate that with respect to x. So this is another shorthand to indicate that you're differentiating with respect to a certain variable. So we have 1 over x plus y squared with respect to x. But the easiest way to handle that, as we saw last time, was to rewrite this as x plus y squared to the minus 1 differentiated with respect to x, and the result was minus 1 over x plus y squared squared. Okay. And I think that's the last one that we finished completely on Monday.
And that's sort of getting around using the quotient rule, like formula.
Yeah, because the quotient rule is never necessary if the numerator is a constant. Yeah, because you could always use it, but then one of your terms up top is always going to be 0, because you're differentiating at constant. Yeah, so if your numerator is a constant, you might as well rewrite it this way, and then use that power rule. but no such luck with the next one. Now, for fxy, because mixed second partial derivatives are equal, this could be done in two different ways. You can either take your fx and differentiate with respect to y, or dfdy and differentiate it with respect to x. So, okay, so your question brings up a good point. Here we have a choice. Which seems easier?
Definitely probably the f of x with respect to y.
Yeah, so taking this partial derivative, and actually I believe at the very tail end of class on Monday I didn't simplify it. I had gone the other way. I just took this and said, well, here, this one, you have to use the quotient rule, and I carried it out. But it's not the best way to go, not the easiest. This one, because now you can think of this as x plus y squared to the minus 1, like we have here, but instead of differentiating with respect to x, now we're going to differentiate with respect to y. So it's going to play out much the same way. And
So what'd you do with your 2?
what?
What'd you do with your 2? The 2 from the 2y.
Oh, no, I'm not using this.
Oh, I'm sorry.
Yeah, so that would have, if I'd gone the other way,
Oh,
then
okay.
yes, I would need that. Okay. All right, so if we just carry this out, differentiating this with respect to y instead of x, like we did up here, what are we going to get? I know you guys know your power rule. It's basically going to be that. All right, so if you have something raised to the minus 1, we'll leave it here or here. How's that power rule work? That's the first thing you use.
Okay, so you're basically multiplying that 2y by, in parentheses, x plus y squared to the negative 1.
We're not using this.
Okay, I was looking at the arrow.
Okay, yeah, because I was pointing out what if we were going to use that to answer your question. But now we're here. Okay.
So is that using the top one? F of
Yes.
x?
Yeah. So
Okay.
all right. So now my arrows are in place. So this is what we're doing. So or I could write this as derivative with respect to y of this.
Okay.
That's what that subscript means. In all these cases, it's differentiation with respect to that variable.
All right. So you'd have bring down the negative 1. That would make the exponent a negative 2. Make that y squared into a 2y.
Yeah, because now you take what's inside here, like you always did in Cal 1 with the chain rule, and differentiate that, but with respect to y. So I'll write it out, an intermediate step here. So now it's x plus y squared with respect to y, and that is, as you said, 2y. So we're going to get minus 2y if we put everything back as a fraction, x plus y squared down below. So, so we see throughout, like here, to identify which partial derivative this is, or to indicate what differentiation process needs to be carried out. That subscript, when it's an independent variable like x or y, it means differentiate with respect to that variable. Okay. Is there any questions about how this one was obtained?
Okay, so that wasn't the chain rule, was it?
Well, yeah, it was.
Okay.
Yeah. Or okay, the way it's often referred to is like the general power rule or generalized power rule.
Yeah.
But that is actually just combining the power rule and the chain rule.
Yeah, I'm just making sure that I'm thinking about this problem right.
Okay. Yep. All right. Now, to get fxy, we have two ways to do it. This is the one we use. If I use this way, I would be differentiating this with respect to x, which I did carry out to a point last time. And this would require the quotient rule. All right. And it's something you can check to make sure after you use the quotient rule and then simplify that you still wind up with this. Okay. As far as second partial derivatives go, what's left?
F of yy.
Yeah, fyy. So differentiating with respect to y twice. So in this case, we only have one option, is to take df dy. So fyy, we have to take this one, fy, and then differentiate it with respect to y. So unfortunately, you got to use the quotient rule. So, so we take this right here and differentiate. But so we're going to use the quotient rule. Just keep in mind that up in your numerator, where you need to take certain derivatives, you have to differentiate only with respect to y. So what would that give you?
So you'd have your f of x would be the 2y.
Yeah, your numerator. Okay.
Yeah, and times the derivative of the denominator, which is just going to be 2y. Okay, I had it reversed.
Yes.
Okay, so you'd have the derivative of 2y, which is 2, and times the x plus y squared.
Yeah.
Then you'd have minus the derivative of the denominator. Yeah, 2y.
Yeah, because it's only with respect to y. Yeah, so you get 2y.
Multiplied by 2y.
Yeah.
Over the denominator squared.
Yeah. Okay. All right, so we have that at least in unsimplified form. Well, there's not much simplification that can be done. So once you simplify that, what would you have?
2x minus 2y squared over your denominator.
Yeah, because you have 2y squared here minus 4y squared here. So, and then you can factor out the 2 if you want. X plus y squared squared. Okay, so now we have everything. We have all the first partial derivatives, all 2 of them here, and then I'm going to box the second partial derivatives. Here's one, there's xx. This is xy or yx, it counts for both, and then yy. So we have 3 distinct partial derivatives, second partial derivatives.
Where did your 2y go?
Oh, wait, which thing? Here?
Yeah.
Oh, because okay, multiply these together to get minus 4y squared.
Okay.
And then I have 2y squared here. So that,
Be a negative 2.
yeah, the 2y squared minus 4y squared to get minus 2y squared down here.
Where's your minus 2y squared?
Oh, it's factored out.
Yeah, I factored out to 2. Yes, so on top I have 2x minus 2y squared.
Okay.
Yeah,
Gotcha.
so, okay. You ever question?
Do we need to factor that like that?
Oh, I don't require that. No. Yeah.
Okay.
Yeah, and I'm pretty sure that MyLabs Plus is not going to be. For certain questions, they might ask the answer to be in a certain form, but for something like this, no.
So we can distribute all that out and that's okay.
Yes, you can. Yeah, and definitely on a test, it's okay because I mean you're under time pressure.
It was kind of tricky on 13.4.
It was.
Yeah, a little bit. When taking a partial derivative of a square root function, it was kind of picky.
Okay. Well, it's a good time to bring this up. If you feel that MyLabs Plus has wronged you, let me know. Because then what I can do is I can look at it and I can see, well, as long as you at least conform to what the question itself was asking, and if it's a case where it was excessively picky, like if it was something like this, for example, and I can see, because I can see your answer. I can check for myself, like, okay, that is equivalent to the right answer, and so I can override the score. Because unfortunately, when it comes to MyLabs Plus or WebAssign, sometimes they get it wrong. Well, sometimes the answer they have, the true answer is just flat out wrong. It's rare that it happens, but it does. And sometimes I've had to like delete a question or something. So final arbiter on that. And also for tests, think about MyLabs Plus or similar systems. They might divide certain problems into multiple parts, if each part is scored separately. But that's your only mechanism for getting partial credit. So if you just have a problem like, okay, compute this partial derivative, and it's credit-wise, it's all or nothing. So on tests, I do give partial credit. For instance, if someone gets a right answer except for a minor mistake, they may still get the majority of the points. But then if it's a more serious error, then there's more of a deduction until you get to a point where the effort is not being made, and then of course you get nothing in that case. And that's why it's very important when you get to tests, especially, do your best not to leave it blank, because that you make it easy for me, but not easy for yourself. So you give me no choice in that case. But if you give me something, I may be able to. If I can justify giving some credit for it, I will. So the more knowledge that you show me, the better off your grade will be. And besides, it's also very important that you show all your work. I've had some people use whatever fancy calculator, like they'll write up some steps that are wrong, and then somehow magically produce a right answer at the bottom. That's called cheating. So, and I do detect that and won't give credit for it. So, nice try. Okay, so the first test is still a ways away, but these are some things to keep in mind. Okay. Let's see. All right. So then, if you have to, if a problem calls for actually evaluating these derivatives at certain points. So as an example, if you're asked for fxx at the point, let's say x is 1 and y is 2. So it's always understood from a problem what order of variables are in, and it's always going to be something conventional like xy or xyz. Then we can just do like you do in single variable calculus, substituting x values into your derivative. You just plug in the required values of x and y. So in this case, this is our fxx, so we just plug x equals 1 and y equals 2 into that. Okay, so we get minus 125, or 125th in that case. Okay. All right, so any questions about carrying out this partial differentiation? So, the important thing to keep in mind is you're custom differentiation anyway from your previous calculus courses, and as you can see, you're using all the same techniques. You just have to keep in mind which variable you're differentiating with respect to. I've had Calculus 4 students still write prime, and I've told you multiple times already that doesn't have any meaning. If you write f prime, I can't tell if you mean df dx or df dy. Okay. Now, one other aspect of partial differentiation that I want to make sure I cover, and this will help to set up upcoming sections. Now, does anyone remember, and maybe you will only remember the term, but this is from Calculus 1, implicit differentiation? Okay.
I remember the name of it.
Okay.
Yeah.
I don't suppose anyone remembers why we have it.
So you can differentiate with respect to y, like you have an equation with multiple variables differentiate.
Yeah, because the reason why it's called implicit differentiation, and this would be a good refresher on certain related jargon that you might not remember from back then, is there's two ways of describing a function, explicit and implicit. And I remember back when I would teach Calculus 2 at our schools, I would, so this is my fourth university that I've taught at, that we would cover that, but it all depends on which textbook you use. So, silence is golden. Okay. So, just to make sure you understand what these terms mean, Now it gives some single variable cases to make the jargon clearer. So either explicitly, so that would be, what do you see most of the time? Y equals f of x, or in this class, z equals f of x and y. So there's a definitive input and output. So you have, so in other words, your independent variables, and that jargon is tested in the first homework, goes into your function, and then other variables are identified as the output or dependent variables. Okay. Now, the other way, and of course this facilitates tasks like differentiating and integrating, is implicitly. So you have some equation of a form, like in single variable, like big F of x, y equals 0. So you have an equation where neither variable is isolated. So one example of this would be, for instance, from a circle, x squared plus y squared equals 1. This implicitly describes y as a function of x, as long as you're talking about either the top half of a circle, because you could solve for y as a function of x and get back to explicit form, but you have to make a choice of square root. So this describes a curve in the xy plane. Now, the thing to keep in mind is any curve in the xy plane can be described using equations such as this. This is always possible. Explicitly, not necessarily, because you have to have y being a function of x, and there are certain rules about functions. Like each x gets mapped to only one y. There's a test. What is the test that a curve has to pass to be called a function? Do you remember that? I heard a bunch of jumbling, but yes, vertical line test is for y being a function of x. What's the horizontal line test for? We have that.
X being playing for the water.
Yeah, and therefore, if it passes the horizontal line test, like if it passes both tests, the function is 1 to 1, therefore invertible. Okay. So often you can solve for explicit. So if it does pass the vertical line test, you can put it in explicit form. Now algebraically, it may be of a tall order, but in theory, it can be done. And we'll see cases like this. F x, y, z equals 0. So this describes a surface. So a surface can always be described implicitly as the level set of some function. So for example, for a sphere, x squared plus y squared plus z squared minus 1 is equal to 0. So I should have written it this way. Because it's customary to write it as something is equal to 0, although you don't absolutely have to. And so this describes the unit sphere. And again, you could try solving for z as a function of x and y, but again, you have to make a choice of positive or negative square root. Because the unit circle, as taken as a whole, does not satisfy, it does not pass the vertical line test, because vertical lines pass through the circle twice. If a curve flunks a vertical line test very badly, like vertical lines pass through it many, many times, then you're just going to need that many more pieces to describe this curve explicitly.
When piecewise functions come into play.
Yes, actually. It's not the only situation, but yes. The other case is like if you have discontinuities. And so you have different formulas for each piece. Okay, now, but the thing is, no matter what kind of function we have, you still want derivatives. You still want like dy dx in the case of a curve. Or the tangent line. Or you want partial of z with respect to x, partial of z with respect to y. So if you're talking about a surface that's described implicitly, you still want to be able to compute these because, all right, let's see how well you can generalize. For a function of one variable describing a curve, you have a tangent line. So what do you think you'd have here if we're going up by one dimension? Yes, it's a tangent plane. Now I haven't talked about a tangent plane yet. I was just throwing out there to see if you guys could get the idea. Tangent planes will be coming up. I'll start covering that on Friday. And then after Labor Day, since I'll be gone, Dr. Lee will pick it up from there. So the same process that you use in Calculus 1 to compute dy dx for an implicitly described function of x and y can be used to, on an equation like this, to implicitly compute partial derivatives of z with respect to x and y. And this generalizes to any number of variables. So you can still describe your tangent line for a curve or tangent plane to a surface. So just as dy dx is the slope of a tangent line, you really need two partial derivatives, like two slopes, if you will, to completely describe a tangent plane. As well as here, you also need a point on a tangent line, like a point of tangency. Here too, you again need a point of tangency, and these two rates of change in different directions, and that completely describes the plane. And that's something we'll get into more later. But I want to make sure to get through today is so that you're able to eventually obtain tangent planes in any case. How to carry out this implicit differentiation. After all, it's likely been a while since you did that in Cal 1. And when you did this in Cal 1, you might have found it a bit of a pain. The funny thing is that after work with tangent planes and so forth, it's actually a lot easier to describe a procedure for implicit differentiation using multivariable calculus notation, using partial derivatives. But good luck trying to use that in the Calculus 1 class. Okay. So what I'm going to do is step through an example. So equation big F of x, y, and z is equal to 0. Actually, I'm going to set it equal to 1. So I'm just taking this 1 and move it to the other side. So, and the function in this case is going to be x squared z plus y squared z plus z squared. And that is equal to 1. So this is my equation that implicitly describes z as a function of x and y. Now, we have this procedure because there are certain cases where algebraically it would be impossible to solve for z as a function of x and y. But aside from what I'm about to do with implicit differentiation, in this particular case, can you solve for z explicitly as a function of x and y? Is it algebraically possible?
I don't think so.
Okay. And if you think so, but how might it be done?
Would you just shrink z to the other side and then divide them?
Nope. Think of what functions of z we have here. We have a z squared. We have a z that is multiplied by something. So if you think of this as, if you think of x and y as just constants. So this is some equation characterizing z. Think of that as your only variable. This is actually kind of equation that you've worked with before. Even well before calculus. Well, like Well, what I could do is I could write it this way. I could factor out the z, and that might make it a little easier to see. And I'll move this term over here.
Could you just divide both sides by x squared plus y squared?
That won't help. Yes, it's a quadratic equation. Especially if I write it this way. You can use a quadratic formula. Now, it's going to give you two solutions. So we're still, so you can't describe z completely as one function. Oh my god, I forgot to move this. What was I thinking? Okay. All right. So, well, at least we've had perfect attendance so far, so that's no problem. So you can describe this whole solution set in two patches, one for choosing a positive square root and the other for a negative square root. So yeah, it just works the same way. So z is equal to, so minus b, so this is your b, and this is your c, and then a is 1. Implicitly there, so yeah, you just have minus x squared plus y squared, plus or minus square root of x squared plus y squared squared, minus 4 all over
2 times.
2. Okay. And there you have it. But even without doing this, so we could try differentiating that with respect to x and y. As you can imagine, with square root and all that, it's going to get pretty ugly. So we're not going to do that. So sometimes, if you leave it like this, do implicit differentiation, the results you get might have a simpler form. And before I complete this example, the last thing I want to mention is, and you all know, or should know the quadratic formula in general. There's actually two quadratic formulas. Here's the other one. Okay. So that's the one that you weren't taught. The way you get the second one from the first one is a trick you've had to use elsewhere. You multiply and divide by the conjugate. That's why the minus plus. So if you take minus b, even the opposite sign, square root of b squared minus 4ac, simplify as much as you can, you get this. And in fact, any technology, any computer, any calculator is actually going to use both formulas in tandem, because if you just use this for both roots, depending on the numbers involved, you might get nasty arithmetic error because of how computers represent numbers. So, like in Math 460, I covered this. So, so hopefully it doesn't blow anybody's mind, but yes, there are two quadratic formulas. Okay. Now, we take this equation and carry out implicit differentiation. Because we have two independent variables, x and y, you have to carry out implicit differentiation twice. First with respect to x, and then we go back and do it with respect to y. So what you're going to do is, you're going to think of z as a function of x. So, and y. But x and y are independent of each other. So in other words, you need to differentiate z with respect to x. When you come across a y, if you're differentiating with respect to x, y is considered a constant. So what you'll get differentiating with respect to z, I'll handle differentiating with respect to x. I'll do that one first, and then you guys could try on y. So for this first term, you're going to get, because both factors here, x squared and z, are considered as both depending on x, you have to use a product rule. So you're going to get 2x times z plus x squared dz dx. Because you're thinking of z as a function of x, you just don't know what it is. So, so this comes from x squared z. Then, the next term, y is treated as a constant because we're differentiating with respect to x. So then all you're going to get from that is y squared dz dx. And then finally, for the last term, z squared, again, z is a function of x. So, and now it's squared. So you have to use a chain rule or generalized power rule. And that will give you 2z dz dx. And then on the right side, you just have a 1, so that differentiate that, and you're going to get 0. So that is what implicit differentiation gives you. And now what you can do is solve for dz dx, because that's the partial derivative that you want. So, and remember, this is how we teach this in Cal 1 also. You take all the terms that have dz dx, you group them together, and then you take all other terms and you group them together. So we have 2xz plus dz dx, which appears in everything else. So we have x squared plus y squared plus 2z, and all that equals 0. So then you can go ahead and okay. So then you can go ahead and rearrange that with, and isolate. So what is dz dx? Bring it home with me, algebra.
It'd
That's
be
all.
negative 2xc
Mm-hmm.
divided by, I can't see it, x squared plus y squared plus 2z.
X squared plus y squared plus 2z. Okay. And that's it. So that's your first function derivative of z with respect to x. Okay. Now, okay, I'll go ahead and get rid of this. Now, let's go back to this equation. Let's get dz dy. So, what happens if you implicitly differentiate this with respect to y, similarly to how I did there with respect to x? What would you get?
You're gonna get x squared zx, or z in respect to x, dz dx.
Or do we want dz dy though?
I mean dz dy.
Yeah. All right. dy, okay. Because x is a constant now. All right. Then we move to the next term.
2y z dy, or z.
It's just z because we're using a product rule on this. So you differentiated 2y with respect to y, and the z stays undifferentiated. But then what's the rest of a product rule? Yes. Well, not 1. You do get a y squared, but because if you were differentiating z with respect to z, you would get 1. But we're differentiating with respect to y.
dz dy.
It's just dz dy. So you think of it like a placeholder. You don't know what this is, but that's the only way you know to identify it. Okay, so that covers this term. What's left?
C squared. So would it be 2z z dy, or with the little y?
What?
Just a Y, right?
Yeah, we're still differentiating with respect to y. So
It'd be 2z and then dz dy.
dz dy. Yeah. So handling the z squared gives you the 2z. Then by chain rule,
Then
Because
what?
differentiating with respect to y in the end, you have to differentiate what's inside, the z,
We'll just do.
with respect to y.
Yeah.
Yeah. Okay. And then equals 0. So then what you could do is same algebraic rearrangement. So this is the only term that doesn't have a dz dy in it, so I write that over here. And then I have zy I can factor out, and it always works this way, just because of how the chain rule is. You can always, there's always certain terms that don't have a zy at all, and then you can just, it only appears as a linear factor in everything else. So x squared plus y squared plus 2z equals 0, and then you can rearrange in the same way to get to conclusion. Which is
Negative 2y
minus 2yz.
over x squared plus y squared.
Yeah. Okay. So now you have enough information as also if you have a single point on this surface, an x, y, z that satisfies the equation. For example, like x, y, z all equals 0 would satisfy. Well, no, it wouldn't satisfy it. Never mind. Well, z. Okay. So for instance, if z equals 1 and then x and y equals 0, that would satisfy it. So that would be like a point of tangency. And then to get basically two ways to change it, to define your tangent plane, you would plug in x, y, and z into both of these. And in a later section, we'll see how to use all this information to actually get the equation of a tangent plane, which is somewhat similar to how you get the equation of a tangent line from single variable calculus. Now, in the last few minutes, I'll describe, here's how, the way you did this here, very similar to what you did in Calculus 1. But in terms of partial derivatives, there's an easier way. It's just not something that is easy to describe to Calculus 1 students, so it's not done at that level. Because you're always dealing with an equation of this form. Some function f of x, y, z is equal to 0. So if I were to take the derivative of this equation with respect to x, and I think of z as depending on x, and x and y are independent variables, that would be the same as partial of f with respect to x, and then when I come to y, I have nothing, because x and y are independent of each other. And then partial of f with respect to z, partial of z with respect to x. What is this? What differentiation rule is this here? That is the chain rule. And that's how it worked in single variable calculus as well. And we will talk more about the chain rule later. But so differentiating this equation with respect to x gives you this. And dz dx is what you want. So you can rearrange this. Dz dx is equal to minus partial of f with respect to x over partial of f with respect to z. Now, I should point out, if you were to think of these two quantities, numerator and denominator, as like ordinary fractions, and try to simplify, yeah, you have like you can think of like the df's canceling out or something, which I'm sure my colleagues would cringe over me saying that, but. Okay, so, and then similarly for dz dy, that is minus partial of f with respect to y over partial of f with respect to z, provided that in both cases partial of f with respect to z must be non-zero for this to be valid. So I could have done this over here to work out that same example, and this is certainly an easier way to describe it because now you guys know how to take partial derivatives. So if you take that function, that the x squared z plus y squared z plus z squared minus 1, and carry this out, you get the same result. And it's probably a lot less mistake prone if you do it this way. Because implicit differentiation, the way it was taught in Cal 1, is pretty tedious. Okay, so Well, that's the end of my time. So we will start talking about tangent planes and such on Friday.